interpolation in the spatial domain. Our objectives is to be familiar with the concept of spatial interpolation. What are the constraints, the limitations, and the issues that you have to worry about, and then look at the very basic interpolation algorithms that are usually non-adaptive and don't care about the structure, the layout in the image. And then we look at some adaptive interpolation methods. There are a couple of classes there. And then we formulate one of those adaptive interpolation method as an estimation problem to minimize the square error. And then overall, whenever you talk about interpolation or super resolution, we want to take into account what are the major issues that affect the quality of an interpolated image. So today we'll talk about some kind of introduction, remarks about interpolation, and then we look at the three basic algorithms that are non-adaptive: pixel replication, bilinear, and bicubic, and then we look at some adaptive interpolation methods. One of them is trivial, and the second one is formulated as an estimation problem. So why do interpolation? As we have seen in the upsampling, for example, it's whenever you are showing your image or your video on a different screen that has a different lattice or a different size or a different scale or a different resolution, you will always need some kind of an interpolation algorithm. And for example, if you look at a single definition video and you put it on an 85-inch or even 65-inch high definition or 4K TV screen, you will start to see basically there is some kind of a distortion because of the interpolation artifacts. And then there is the image inpainting, and that's basically error concealment. For example, when we transmit, if you have a satellite TV at home, or even you have a poor internet connection, and they are watching some live or some video on demand, and in straight case, it's more obvious because if there's a storm outside, then you see sometimes you have this kind of blocking artifacts. You will have some kind of areas that are really green, like blocks. When we talk about compression, we'll understand where these coming from. But in general, you'll have these blocks of green and black, and some of the high-end displays, they have an error concealment. So they detect there is some missing blocks because of the transmission or networking or the streaming, or because of maybe hardware error. And then there is an error concealment algorithm. The error concealment algorithm is nothing but really an image inpainting or an interpolation. You look at the neighboring pixel within the frame, and if you have a video, you look also in the neighboring frames. And there are most of the video error concealment or interpolation algorithms out there. They look at 2 frames in a video, or maybe a frame before, a frame after. But there are some recent methods where they look at n frames, and you can imagine basically you have much more space to pick your pixels from, so you have a better estimation in this case. And then whenever you have a geometric transformation, the most obvious one example, when you have a multi-camera, you have the easiest, like a stereo camera. You have 2 cameras, and definitely they are not lined up very well, and then you have some kind of a distance shift between the axes of the 2 cameras. So you have some kind of a geometric transformation. If you are using this to regenerate a depth-based image, for example, and then that process, we call it DIBR, depth image-based rendering, DIBR, because of some occlusion, you will have some kind of holes around the edges and around the occluded area in the scene because of the 2 camera effect, and maybe because of motion in the video. Even if not a video, just an image, or a scene, a static scene, there will be some occlusion there. So now when you do this kind of hole filling in that space, then what you're really doing is really interpolation, because you have a lifted view, for example, and you have a depth, and you're really trying kind of to fill in these holes because of the occlusion using interpolation. So it's very different applications. Each one is caused by something different. But at the end of the day, what you have a known lattice, a known number of pixels, either they are in the same frame or different neighboring frames, or maybe it's a different view of the same scene. And you are trying to estimate what these missing pixel values are from the given pixel values. So the formulation is very similar. So throughout the lecture today, the notation we will be following is what we have in this slide. So on the left-hand side, we are just really kind of spreading these pixels. We have 2 by 2 pixels with these filled in black circles, and these are the low resolution. These are the pixels that we have at this resolution. As an example, on the left image, this image in here is an image I took it in Budapest. So it has in the upper we have this kind of like a uniform areas or semi-uniform with the cloud in the sky, and then you have very, very detailed, basically because of the buildings for the rest of the image. And then if you really have a higher resolution image, as on the right hand side, we are already upsampling. In this case, we are inserting one pixel between 2 consecutive pixels, either horizontally or vertically. Then we will label these new resolution, these new pixel locations as an empty or blank blue circle. In this case, this is unknown values, and our job in interpolation is to find the values for these new pixels. And all what we know in this example, in the upper, just a toy example, we have 4 pixel values, and we are really trying to find the values for the new 12 pixels. And that's basically kind of what the formulation is in this case. This is a video, I like always to show it from a paper that will do image in painting. Let me try to see if I can play it here. This is an iterative method where you can see, I hope you can see it, where basically it's every iteration and there is a minimization of a certain error. It's not showing very well. Let me try again. Okay. Let's try last time. Yep, I expected it not to work. So at least the image that you see, it's a freeze. It's a frozen slide. Sorry for that. Basically, this is an iterative method that every single frame of this video is just basically the in-painting algorithm is really trying to use the existing values surrounding this individual who's jumping to really in-paint these videos, and it's just working throughout the whole area. And you can see basically it's iterative algorithm, but it's really doing a good job. And how we can decide on a good job is from the perceived end image, or we don't really, it looks natural to us. Although if you really compute certain quality metric or certain perceptual or natural statistics, then it may not really fit the profile. And we'll talk about those in image quality assessment later on. I know I stopped sharing for some reason. I hope, just give me a second. Okay. So this is an example of an image in painting algorithm using uh, interpolation methodology. Another scenario when you have an image warping as kind of warping application in this case. Yes, definitely. When you look at the image on the right hand side, you can see on the feather basically there are some kind of distortion, some artifacts happening. But overall, how can you minimize those artifacts? So you do the interpolation within this red area, actually for the entire center of the image. But you can see the artifacts are most obvious around the feather because of the texture that the feather has. So some remarks that are really very important when we talk about interpolation. The idea of having a perfect interpolation doesn't exist. So always you have artifacts, always you have losses, and the job is to minimize these losses, to minimize these artifacts. If at the end of the day it's for viewers, for a human to look at the image, then the quality or the error that you're already trying to minimize is the perceived error based on some perception, perceived quality. And we'll talk on Thursday and next week about image quality assessment algorithms. If the application is something else like segmentation, classification, and so on, then those should be taken into account as the error to be minimized. There's the artifacts issue. And then, although the third bulletin here, although the interpolation, you start with a known subset of data, and then you're really trying to estimate new data, and then the very basic relationship between the two data sets, there is a correlation between them. So that correlation, you can model that as a linear operation. But also there are many cases where you have some other information. If you have context information about the image, whether it's really a computed image, a landscape image, a sport image, a portrait, this kind of context level information can also be very helpful in designing your interpolation algorithm and iteration. And then the main focus in interpolation, we really try to find the intensity values or color values. We don't really, like in a video, for example, we don't really try to interpolate in the motion axis, for example. Although in videos, for example, the main one of the main attributes in a video is that, or the physical content of phenomena is the motion itself. But usually we just limit our interpolation to intensity values and color information in this case. So let's really get into it, look at spatial interpolation. Whenever we do resampling, whenever you are really trying to relocate the image pixels into a new lattice, whatever that lattice is, either is resulting from zooming in, zooming out, rotation, sub-image registration, motion estimation, and we'll see in video coding or video compression. In all of these, and we'll study in much more detail video compression and motion estimation. Whenever you do this, then you need spatial interpolation. And it's really worth it to spend time to look at this, what we refer to as Chroma subsampling. And it's very common. You see it if you look at video codecs, for example, if you look at some displays, then you have this idea of what really Chroma subsampling. And Chroma subsampling, usually what you have 3 digits like this. So you have 4, 4, and these 3 digits, they mean something. So in the first column, we have the loma, and that's the luminance. And in this case, we have the 4, for example, the photoresidence number. This refers to the size of the sample. So what this means is when you are looking at your block, you are looking at 2 rows and then 4 samples in each row. So that's the first number 4 on the left-hand side. And then the next 2 numbers, 4 and 4 in this case, they are really about how much correspondence between the chroma samples and the loma samples. So in the first case, when we have 4, 4, and 4, so you have the first row for the lumina, for luminance, and the other 2 for the chrominance. And this means you don't really have any subsampling. It means the same resolution you have the luminance, you have it in the chrominance. That means you have really 4 and 4. You have a 4 in the first row and 4 in the second row in the chrominance. You can see in here, you have the same resolution in the luminance and the chrominance. You are not really doing any chroma subsampling in this case. Compare this to the second case when you have 4, 2, and 2. Again, the first 4 is for the luminance, and then the second one is 2 it means that in a 4x2 array of pixels, the 4-to-2 chroma subsampling, it means that you have half the chroma of the 4-4-4 case, right? And that's what you have in here. So what you have as you go in these 2 pixels, you have the same chroma. The next 2 pixels have the same chroma, and then vertically you have a 2 subsampling. So that's why we have 4, 2, and 2. So you can think of it as basically you have horizontally you have 2 samples in the chroma, and vertically you have 2 samples in the chroma. And so that's basically it's what you have. You have the chroma subsampling in this case is half what you have in the 4-4-4 case. And then if you contrast that with the case when you have 4-2-0, 4-2-0 means that horizontally you have, going horizontally this way, you have 2 samples, but vertically you don't have any subsampling, any subsamples. You have the same color. So as if the second row is really not necessary. So you don't really need the second row in this case for the chroma subsampling. That's why you have the 0 in this case. So that's how you can think of this chroma subsampling in here. Of course, what this means in terms of, let's think about it in terms of compression, for example. In the 4-2-0 case, what you need 4 different values to represent your luminance, but you need only 2 values to represent your chroma. And in the luminance case, you have in each row, you have 4 intensity values of the luminance, and then you have 2 for the chroma for each row. So you have 2 by 2, that's 4. And then in the 4-4-4 case, you will have, for each row, you have 4 different values in the luminance, and the same thing in the chrominance, you have 4 different values. So you can see in 4-2-0 is you are really having a quarter of the color information or the resolution in the color compared to the 4-4-4. In the 4-2-2, you have half the resolution or the information in the color compared to 4-4-4. So you can think of this as a subsampling. And this is usually, we use it because we are less sensitive to these variations in the chroma channel compared to the luminance channel. So I just want to show you basically this as it will be showing up in the compression case. So questions, why is the last one instead of 4-2? So think of everything we look at as a block, like you have a 2x2. So right so you have a 2x2. Do you assign to it 4 numbers? Do you assign to it 2 numbers, or do you assign to it 1 number? Right? If you assign to it a 0 number, that means there is no chroma. Right? There is no channel for chroma in this case, or 0 for luminance. So think of it as 2x2, and then you have 4. And then now the question is, do you have another 4 chroma, or another 2 chroma, or another or 1 value? And then now why do we have 2 digits, like the 2 and 2 or 4 and 4 on the right hand side? Basically, that will tell you the chroma values, are you going vertical or horizontal? Is a convention. So that's what this is really telling us in this case. And why didn't we have just basically because if you go to 1, that means you don't have transition, right? So the 0 in the 4 to 0, that means we don't really have any more information in the second row. It doesn't really tell us anything in the second row. It's more of a convention than anything else. But it's really the whole in image processing. We'll see that in coding and compression, especially motion estimation, we always think of a block, a square block, and in this subsampling, you can just think of 2 by 2. And now the question is, in the luminance, if I have 2 by 2, that means I have 4 different intensity values, or maybe similar, but I have the freedom to have 4 different samples. And then do I assign 1 number for everything for the chroma, or 4, or 2? And now the 2 values, are they going row and row, or column and column, as in the case in this specific example. So that's the reasoning for this convention. And then the table on the lower left corner is just showing what are the most common subsampling, chroma subsampling in different codecs and different displays, and what kind of visual impact it has. The most major one basically on the PC, because we have text, and usually we don't really have any. We'll study this more on Thursday. We don't really have any masking because we don't really have much motion, most static windows on our PCs. In the movies, we have more of motion that really do the masking job for us. Same thing for the other content in this case. But these are kind of standards. Do all content stick to this? No, I think if you look at the content, right click on YouTube for different videos, you will see all kind of different chroma subsampling, as far as I know on YouTube, unless they changed it recently. So let's look at the case when we have what is interpolation? The interpolation, and this is something we briefly talked about when we did upsampling, but this is where we dig a little bit deeper. So the whole idea in here, you have your continuous signal, you digitize it, and then you convert it back, you get your G hat, and then the question is, how can you get from G samples an estimate for G, which is G hat in this case? And then you remember, G, basically we have these kind of shifted deltas, that's what we have in here. And then what we're really trying to use a kernel, that's really a reconstruction kernel. We look at this as a U of X and Y. And this is a convolution here, and basically we have a delta, so it's simple to say at every single sample in G, we really multiply it by a shifted kernel centered at that sample location M and N in this case. And the simplest one we looked at, or the ideal one, is the sync function, right? So that's basically what we showed in the sampling lectures. When we have a sync function, you can really perfectly reconstruct your signal, but not realistic because that means we have it's band limited. It means infinite spatial support, so it's not really practical and not realistic. So we need to have some kind of an approximation of this sync function to make this happen. And that's basically bring us to the pixel replication. So as the name states, what it means, if you have a known value of a pixel, and then next to it you have a new pixel that you don't know what the value is, just repeat that pixel value that you know. Just keep repeating it until you hit to the next known pixel value. And that's what we refer to in the 1D case, and your undergrad probably, it's called the zero order hold. Basically, you hold that value same as it is until the next sample, and then you have a new, you hold it, and so on. So equation-wise, the reconstruction kernel will be 1 whenever I am within a certain sample, and 0 otherwise. So the best thing is to look at as an example. This is a 1D case, but it really illustrates how things are happening. So this is the reconstruction kernel. It's between 0 and 1, and then between the value for x larger than or equal to 0 and less than 1, the value is 1. What from this equation here, what we have this, right? So which is really the shifted U, the kernel. Imagine that this is our discrete signal G of M. So we have a sample at 0, a sample at 1, a sample at 2, a sample at 3. And what we are showing in here are the magnitude for these samples. Imagine that our image is only one row. Right? So what this equation is telling us, this is the zero order hold. You take U of X, and then to go to this sample in here, and then you just multiply it. That will be the value, and then you get to the next one. You shift, multiply with the new value, go to the next one, multiply, next one, multiply, and so on. And this becomes our reconstructed signal G hat in this case. So you can imagine it has this stair-like structure where every sample holding its value until the next sample, and so on. So that's the zero order hold, the replication. In images, what that means for this specific example, if L is equal to 3, that means I'm inserting 3 minus 1 as 2 new pixels between two adjacent pixels. Again, these are known. These are known values. These are the new pixels. Right? So we are trying to estimate the values for such pixels. So the pixel replication, for example, will say, take the value of G1 and then repeat it for all these pixels in here until you get to the next pixel. Then now this pixel value in here will be repeated here and here. This one will be repeated here and here. And this one will repeat here and here, and so on. So you can see basically now a single pixel value, it could be represented in a 3x3 block in the new image, right? And if we take that image of Budapest image and then we downsample, so the original image was 512 by 512, we downsampled to 256 by 256, we downsampled to 128 by 128, and then we downsampled to 64 by 64. So we have 3 levels of this downsampled image. Now what we will do in the next is to upsample using pixel replication. So remember, this will refer to as image 0. This is image downsampled 1, image downsampled 2, and image downsampled 3. So if you take the image downsampled 3 and you up, it is the same as the one that we had, 64 by 64. And then now you interpolate using pixel replication to this 128 by 128. And this is the image that we'll get. If you look at the PCNR value is 14 dB. Now take the image down 2, which was this one here, upsample it to get this image here. And the PSNR is 16. So the PSNR is between this image in here and this image in here. Otherwise, we have to be comparing apple to apples in this case. And then the next thing is take this image and then upsample it to get this image in here. And the PSNR in this case is 20 dB. Okay, so let me stop here. So what do you notice about this image? We'll look at many examples, but let's just look at this image in here. If you look around this areas in here compared to this areas in here, look at this area in here compared to this one here. So you have this kind of an jaggy kind of edges, right? They are not really straight. There is some kind of interruption happening. And we'll zoom in some of these images in a minute. However, something that you should really be able to notice in here, look at this image on the left-hand side and this image on the right-hand side is not blurry, right? It still has that kind of sharp effect. So the artifact from pixel replication, you don't really, as this kind of jaggy edges, but you don't really lose in terms of the sharpness of the image. So, which is a good thing in some aspect, but we'll hold on to evaluate after we finish a couple of other methods. So the pixel replication, you can see, is very simple. Just repeat the pixel values until you hit the next sample, and then you have a new sample in the memory, and then just populate into the next sample and so on. So we can do a little bit better than that. And why? Because in here, what's happening, if you have edges or you have some kind of jump in the intensity values, what you are really introducing quite a bit of artifacts, right? Because usually you expect this pixel and this pixel in here, and actually expect this whole area 4x4 pixels, which is really small nowadays, high definition resolution, to be really highly correlated. So there is not really much of variation in the content unless you have an edge. All right. So this replication, the artifacts, it really brings this kind of discontinuity, or bring this kind of a high frequency or edges into the content, and that's why you have this sharpness is not really affected, but there is this jaggy effect in this particular image. Unless you really look at certain details, you may not even observe that this is an upsampled image. So that's why bilinear, as the name states, is really trying to look at, take the neighboring pixels into account and use a linear combination, an average, if you like, of the neighboring pixels, right? That average can be a weighted average. So in this case, what we call it the first order Hall interpolation, our kernel is this image, 1 minus absolute value of x in the x direction and 1 minus absolute value of y in the y direction. The best thing just to look at it in the 1D case. So this what, as you can see, before we had only operated between 0 and 1. Now we are looking at between -1 and 1, right? And we are really trying to take into consideration the neighboring samples. So again, we have the same image as, the same signal as before. Imagine it's just one row image, and these are the samples. And then what we do, again, the same shift as before, take each sample, take each kernel, shift it to that sample, multiply, and then that's what we have in here. So you have, see, in the dotted line, this is the multiplication of the sample. Again, this is the shift, multiply by this sample, you get this dotted line, shift the kernel to this sample, you get this dotted line, shift to this sample, you get this dotted line, and this is what you get. And now basically you add these values together, right? And that's when you get something like this. So what you had before in the pixel replication, you have a stair-like. Now you have some kind of linearity between different sample or between different pixel locations. So now you can see basically in the reconstruction, we are really doing a little bit better job in not having discontinuities between adjacent samples. So what that means in the two-dimensional case, what we have in here is our weights, and those will become more problematic in the bicubic. But the simplest thing to look at is these weights are proportional to the distance. So if I'm using a pixel that's really 2 locations away, then the weight should be lower than if I'm using a pixel that's really 1 distance away. So that's basically the whole purpose of these weights. So this is an illustration of what's happening. Again, we have G1, G2, G3, G4 are pixels from the low resolution image, and the blank empty circles are the new samples or the new pixels. We're trying to estimate them. So if I'm estimating the value for this pixel in X in here, then I need to use the 4 samples. So I'm using G1, G2, G3, G4. So now I'm using 4 samples. In the previous case, in the replication, we only use G1. So you can see there's quite a bit of difference in here. So on top of that, I'm not using G1, G2, G3, G4 with the same weight as if we're estimating, for example, this pixel, right? Because the distances are different. So in this case in here, for this distance, for this pixel, I'm using G1 with a delta M and delta N sample weight, and then 1 minus delta M and 1 minus delta N for G2 and G3. And then for G4, I'm using in both direction 1 minus delta M and 1 minus delta N in this case. And that's what we have in here. Okay. So now you can see the pixel that most contributing with the highest weight will be G1, right? And the deltas basically are given with this relationship in here. So you can imagine in this case, what I will have the delta M and delta N as 2/3, and then 1 minus delta M is 1/3, and 1 minus delta N is 1/3. So I'm having less weight to those who are farther away and more weight to the ones closer by. For this one here, for example, if I'm estimating this pixel, then I'm using G4, higher weight for G4 and lower weight for G1, which is the reciprocal of this equation in here. So that's the bilinear. Let's look at the impact of what we are doing in here. So you can see that the idea in here is really to use more of the neighboring pixels, have a much more graceful transition in the intensity values between these pixels. So again, if we do the same image as we had before, but now we are interpolating using bilinear. So we are obtaining these images using bilinear interpolation. And then I think the next slide, yes. So you can compare this one with this one here. Okay, I have a comparison later. So let me zoom in if I find any. So this one here is using bilinear. So this one here is bilinear. And this one is replication. So you can see quite a bit in the replication one, we have these jaggy edges when we zoom in. In the bilinear, it's much smoother, right? But at the same time, the right away perceived artifact is this blurriness, right? And that's basically because we are averaging, it's a weighted average. So we are really reducing the sharpness in the image. But you can see there's a big difference between the two images and between the sharpness and the blurriness in this case. The tiny details in the images, because remember, this is going from 256 to 512. So we are really inserting only one pixel between every two adjacent pixels. So for every 2 by 2 in the 256 by 256, we are adding 4 new pixel values, right? So the effect on those tiny details, like look at this column or this rod in here, whenever you have straight line, this one here, for example, quite a bit in here. This whole thing is messed up in this case. This one here, and so on. The ones in the distance, you cannot really observe them very well. And then you compare that with what we have in here. This is smoother, basically, effect, as you can see. Okay. Again, if you look at this from a quality estimation or a quality measurement, the PSNR is 21 dB for bilinear. For the pixel replication is 20 dB. So the question is this 1.7 dB a good reflection of the true difference between the perceived qualities? And the question is, PSNR is not. So we will study this more on Thursday and next week, where do these numbers really mean much? And we'll study more. I cannot say yes or no now. We need to really study this. The only thing I could say, the correlation between the PSNR and the perceived quality by humans in the human vision system is not high. So PSNR is not really a human vision system based quality measure. So yes, the question is, how is color impacted by these methods? Yes, because whatever you are doing in the luminance domain you will be doing in the chrominance domain as well, right? And now, remember the chroma subsampling, it depends on what that chroma subsampling is. Whatever the default is, you take each channel and you just basically do the same operation that you're doing, either as the bilinear or replication and so on. So you do the same operation here in each channel. So in the bicubic, as the name states, now we're already moving a little bit more complicated. And the idea in here, can we have some kind of constraints on the first derivative, which means that when I go from between -1 and 1, before I had this kind of, at -1 and 1, I have some kind of a discontinuity. Now, can I have a constraints on these end values in the first derivative? So I have some kind of more of a continuity in the first derivative, which means that I want to get more beyond just the 2 adjacent samples. Can I go to the 2 next samples in that case? So, and that's basically kind of the general equation for bicubic interpolation, where I'm looking at expression for x between 0 and 1. And now I'm looking at this between 1 and 2 as well. And I have these parameters in here, 8 of them, that will determine the values for my bicubic formulation. So these are the constraints. The additional one we have, so this one we had it before, basically. Now we didn't have it before, so now we are really trying to say that as you approach sample 1, so you have a continuity in the kernel, but also we're adding this to have a continuous in the first derivative as well. And if we have all of these constraints, we can rewrite these equations. So we have these 4 equations with these 8 unknowns, right? So if we do it for the continuity from right and left, then this is from left, from right, from left, from right, from left, and from right. Then we have 7 equations. And now we have 7 equations, 8 unknowns. And these are very simple arithmetics, so I'm not going to go through these. But we add an 8th equation, which is really a user specified. And the original paper had A2 equal to -12. That seems to give the best perceived performance in the images. And that gives us this kernel. This is the 1-dimensional bicubic kernel. And if you take the 2-dimensional one, is a product of these 2 1-dimensional one as separable functions. Before we get to the images, if you look at the kernel, you can see before we had something like that, and then we had something like this, and now we are really getting closer and closer to having something similar to a sinc function, right? And what that means is we have more of, as I'm close, so this is the center where I am. As far as I'm close to this distance-wise, I have a high weight. This weight go lower, lower, and then from the other, I use also the other neighbors. So not only the immediate neighbors, but also I'm using the next neighbors as well in my estimation. So you do the same thing, and then you have these kind of dotted lines, multiply it by the sample, do the same thing, move to the next sample, multiply, and so on. So I'll end up with something like this in here. So you have more and more gradual transition in the intensity values on the x-axis. I want to really just leave this for you to read. There's not really much details in here. It's just how you can really construct the 2-dimensional one, which is really a product of the 2 1D in the x and the y directions. But what I will show you is this one here. Yes, this one here is basically a algorithmic view of what's really happening. So you can imagine what in the replica we have 1 pixel repeat. In the bilinear, you look at the immediate neighboring pixels, and that's what in this case, for example, if I'm estimating this pixel in here, I'm looking at G6, G7, G10, and G11 in my bilinear. And now if I'm looking at bicubic, I go to the next level of my neighbors. And that's basically bring this G1, G2, G4, which is a 4x4. So I have 16 pixels to estimate from in this case. Now, each one of them have a weight in the x-axis and the y-axis. So I have two weights in here that really depend on the location. So for this pixel at the center that I'm trying to estimate, G6 will be the highest weight, and then G7 and G10 and G11 will be next, and so on for the surrounding pixels. And that's really what the bicubic is so you're trying to use more and more of our neighbors because of the high correlation between the adjacent pixels. So let's look at the examples. This is the bicubic one. So this is 21.7 dB. This is the 512 by 512. What we did, we took this image, we upsampled it. We took the corresponding image to 128, 128 in the downsampling. We didn't really upsample this one to this one. We didn't do that. We took the image, downsampled one, 128 by 128, and then we upsampled to this image. And the same thing for this one. We didn't really get this from here. The one we downsampled to 256 by 256, we upsampled it back to 512 by 512. And the reason why we are not really upsampling here, there will be a propagation of error that will make basically the final image looks really, really bad. So we're just using this example to only show you upsampling by 2, what the impact will look like. So I think we have some comparison, not here. Yeah, here. So let's look at these examples in here. So we have pixel replication on the right-hand side, the original image on the left-hand side. And you can see in the oval here, the red one, you can see what's happening. You can see even these streaks, horizontal ones, right? Because we are really doing replication of intensity values. You can see the issues happening in here, right? You can see what's happening here. Everywhere, you can see the effect of replication in this case. In the bilinear, I think this should be bilinear, this one, not bicubic. Mainly what will happen, it's to less extent in the bicubic, but in the bilinear, you can see basically there is a blurry effect. You can see there's a blurry effect happening. The sharpness of the edges is not there. So that's basically what we should look at in this upsampling of images. Okay, questions? Okay, so if you look at all of these, the main problem that we are facing is whenever we have edges, if something is really uniform, actually I forgot to mention this. If you look at in the river here, right? Same thing in here. This is kind of a uniform areas. If you look in this part of the wall or this part of the roof, you can see whenever we don't really have edges, things look reasonably good quality. So the problem is in this interpolation or super resolution, whenever you have edges, as really it's very obvious. So and that's when you have quite a bit of artifact being perceived in this case. That's why we say artifacts in interpolation and super resolution are mostly edge-related. If you can extend this to even to videos, and what will be the problem with if you, for example, when I insert one whole frame between two consecutive frames for any reason, you can imagine the motion becomes also an issue, right? Not only the edges, but also the motion in the video becomes a problem. So that's really one issue. The second one is maybe the algorithm that we studied so far, the replication, bilinear, bicubic, or a combination of some of these, don't really adapt to the content in the image. Certain parts of the image, they work very beautifully. For other parts, when you have edges, it doesn't really work very well. So there's the adaptivity issue over there. And then at the end of the day, if you have a real-time operation, then real-time processing or cost in terms of time is an issue if you have such real-time applications. These are kind of the things you have to look at when you study what algorithms you want to use. So now we look at, we know that edges are problematic, and people have been working on having edge-based methods. So the first one is really a very intuitive one, or a trivial one, to say, and we call this the explicit edge detection-based interpolation. So the idea in here is illustrated in this example. So imagine, again, these red pixels are low resolution known. These are known pixel values. These are unknown. Imagine you have edge one. Don't worry about the other edges. And now if I want to estimate using bilinear, for example, the intensity value for this pixel, I'm circling in blue in here, then I have no problem using this pixel. I have no problem using this pixel. I have no problem using this pixel. I have a problem using this pixel here. Why? Because it lies on this other side of the edge, right? So now that will be a problem, because that will be a totally different value than, most likely, than these three other pixels that on this side of the edge. So it's not really wise to use this pixel in my estimation. And the same thing for edge 2, edge 3. You can imagine you can pick any pixel and there is an issue because of these edges presence in the image. So what people have been using is the following. One of two strategies. So the most trivial one is to say, I will do my interpolation, and then I will have an edge detection algorithm afterward. And then once I have the edge detection, then when I have an estimate of the edge map, I go back basically and I try to correct my interpolation that way. Or I can do it vice versa. I can start to do an edge detection in the low resolution image. I have an edge map, and then I do interpolation, keeping in mind that I have these edges. So now I can use this information on the edge map to know which pixels I use to estimate what pixels. In other words, if I know an estimate of edge 1, edge 2, edge 3, then I will know that I should not really use this pixel to estimate the value of this pixel using bilinear interpolation, for example. And so here are some, these are all ad hoc approaches, and then we'll study something more systematic than this. So in this example, example 1, let's assume that I have G1, G2, G3, and G4, and I would like to use them to estimate the value for this pixel, Gx. So now, just assume that I have this edge 1 in green, and I can see from edge 1 in green that G1 should be questioned if I want to use it or not, right? So G2, G3, and G4 all exist on this side of the edge, so there's no problem in using to estimate Gx, but I cannot use G1. And one ad hoc methodology is to say I can generate basically a G1 prime, or an estimate of G1 on this side of the edge by taking an interpolation between G2 and G3, right? Or a midpoint or a median between G3 and G2. And especially, let's say, the midpoint between G2 and G3. And then now this pixel here is basically my pseudo G1. So I can use this value in here, the midpoint between G2 and G3, as my G1 in my bilinear interpolation, as an example. So that's one ad hoc approach. And this slide just explains what I just talked about. The other example, example number 2 in here, imagine that I have an edge 2, which is in red, this one here. And now, again, I want to estimate the value for this pixel, but the algorithm basically is using G1, G2, G3, and G4 as a if I don't really care about edges, I will just use these four as they are. However, G1 and G3 are on the other side of the edge. So I have to question the use of G1 and G3. So one ad hoc approach is to say, I can create pseudo G1 and pseudo G3 by extrapolating between G5 and G2. So if I extrapolate in here, I have G1 estimate, extrapolate between G4, G6 and G4, I have an estimate for G3. And then now I use these two estimates to find the value for Gx using bilinear. So you can see we can come with tons of other ad hoc approaches, and because they're using the edge information. What is an alternative, a more constructive alternative, is this method. So this method is called the New Edge Directed Interpolation, or NEDI for short. And this is the paper, and I have the paper on Canvas for your reading. And in here, this is really linear adaptive interpolation. So it's simple in terms of linearity. It's adaptive to the content of the image. And then it really look at the local correlations between different pixels without really using the edge map explicitly. Which is, it removes that ad hoc approach. And the whole idea behind this method is that it looks at the interpolation as an estimation problem. Before we dig deeper into this, let's look at what least square estimators are to refresh your memory about those. So imagine I have C11, C12, C13, C14, and I'm interested in estimating the value for C1. Okay. So now I want to find a linear estimator that estimates the value for C1 from these four values. So a very simple formulation. I have these four coefficients, alpha 1, alpha 2, alpha 3, alpha 4. And then I have C11, C12, C13, C14. And then basically there's an estimate of C1, right? So I could generalize this for every single new pixel C1 in my image. So I have C1, I have C2. Imagine I have M by M, right? So I have CM square, right? So I have M square pixel values, and I want to estimate each one of them using the same four coefficients, right? Alpha 1, alpha 2, alpha 3, alpha 4. However, what I'm using to estimate each one of them, C1 will use this row of coefficients, these four. C2 will use this one, and so on. CM square will use these ones in here. Okay. Yeah, there's a question, I missed it. Can edge-based interpolation be done in runtime? Yeah, I mean, there is quite a bit of parallel computing could do to make that happen. However, it's really, there is no control whatsoever on minimizing the artifacts in the methods that we did. There is no guarantee basically in these ad hoc approaches, the trivial edge-based methods that will give you an optimal solution or even a quasi-optimal. This one here, at least in the square error sense, the least square error sense, it is minimum. So that's a better approach than the previous ones that I quickly went over. So in this formulation I have in here, this is the error. The error is really the difference between, so this is the difference between our estimates, right? Between the true values, C1, C2, or CM square, and the estimates using alpha 1, alpha 2, alpha 3. So I could label the first one as Y, this matrix as C, and then my alpha vector as alpha in this case. So the error is the difference between Y and C times alpha. So if I look at the sum of the square, this is the sum of the error square, or it can be this vector transpose times this vector in here, and then I could really have this expression in here. So which is really Y transpose Y minus Y transpose C alpha minus and so on. So straightforward calculations. So in this case, I have now an estimate or formulation for our square error. And then if you look carefully at if you look at this one here, you look carefully at these two terms in the middle, and if you really do them by hand to see basically what they represent, you will see basically these two terms are really equal. So I can really represent these two using -2 alpha transpose C transpose Y. And this one here is nothing but what? It's a quadratic form in terms of alpha, right? So it's a quadratic form in terms of alpha. If you do the product between these two, these four terms, you will have alpha squared, basically. So in that, what that means, if I take the derivative of this error square with respect to alpha and equate that to 0, then what I will get, this will be a derivative 0. This one here will be minus -2 C transpose Y, because I'm taking the derivative with respect to alpha. And then this one, because the quadratic form, it will be 2 C transpose C alpha, right? Because it will be alpha square before. So this is really quadratic in terms of alpha. So now I equate this to 0 and here, and then that will give me this expression. And now I have a general expression for what that least square estimator alpha should look like in terms of C transpose C and Y. So now I want you to keep this on the side. This is just a derivation of the least square estimator as is, and then we'll use that in a minute. So the best way to explain this is to go to, yes, here. So let me go here. So now we have a function. You look at in terms of coding in MATLAB or Python. If I give it 4 numbers, right, that are C11, C12, C13, C14, it will give me basically an estimation for C1, right? So now I have that tool, right? So now imagine that what we have in this diagram, these red circles, these are the low resolution samples. These are the ones that I know already beforehand. These are the ones I'm using to interpolate. And now I'm trying to do upsampling by 2, L equal to 2, which means that between every 2 consecutive red samples, I am inserting a new sample, a new pixel. Okay? So now what I have is the following. Just focus on this blue square. In this blue square, right? Now, I have 4 corners. I could label these as C11, C12, C13, C14, right? And now I can have an estimate of the center pixel C1. That's the one I know, right? So now you can see that I can use basically these 5 pixels, right? C1 and those 4 corners to estimate alpha using my alpha equation from the least square estimation 2 slides back. I can do the same thing. I could come here to this square, right? And now I have these 4 corners, and I call them C36-1, C36-2, C36-3, C36-4, to estimate the center, which is C36. So now, minimizing the error between the true value for C36, right, and the estimation using in the least square sense, I can really find values for alpha, our weights, our linear weights, alpha 1, alpha 2, alpha 3, and alpha 4. So now, why I call them C36 in this case? Because my green window, the 6 by 6 window. So I call this a training window, meaning that I would like, in this specific example, I'm using this training window, which is 6 by 6 pixels, right? I'm using the relationship between every single pixel in this training window and the neighbors in the corner for every single pixel, as we did for C1, You can do for C2, you can do for C3, C4, C40, sorry, C20, C30, all the way to C36. So I can use that. I can use, so now my Y vector in my setup is how long? It's 36. My C matrix will be 36 times 4, right? And my alpha is 4, 4 by 1. So now I can use these to minimize the error in the least square sense and have a value for alpha 1, alpha 2, alpha 3, alpha 4 in this case. Now, so that's, now I use this my training window. I found using the least square estimation the values for alpha 1, alpha 2, alpha 3, alpha 4. Now I use this alpha 1, alpha 2, alpha 3, alpha 4, and I come back to estimate the values for the pixel. So imagine I'm looking at this B. And now my estimate for this value B will be alpha 1 times this pixel plus alpha 2 times this pixel plus alpha 3 times this pixel plus alpha 4 times this pixel, right? And I can do the same thing for all these new pixels, all these new ones. I know alpha 1, alpha 2, alpha 3, alpha 4. Then I can really have an estimate for all of these. I hope this is clear. And now once I have the values for these new pixels, I will call these pixels, I will classify them as pixels B, capital B. Now, remember, when we have, these are known pixels, right? I am inserting B, I'm inserting pixels here, I'm inserting pixels here and here, right? The first round, I find the values for these pixels. Now the next round, I would like to find, so what's special about these pixels? Why I call them B? B pixels, they have known or neighboring pixels with known values in the corners, right? All the B, we have these corners, right? What about E pixels? They have two very adjacent pixels horizontally, and then two basically that are estimated. So what I have in here is a B. What I have in here is a B. So the E pixels, they have two known ground truth pixel values and horizontally, and then two on top and bottom that are estimated. And vice versa for the A ones. The A ones, the two on the top and the bottom are ground truth. They are known values from the low resolution. The one on the right and the left are estimated, right, which are the B values. So once I found the B values, then now for E, I have the four neighbors, two Bs and two from the resolution. Now I can use the same alpha 1, alpha 2, alpha 3, alpha 4, apply the same linear estimate. Once I have the E's, then for the same thing, I can do this in parallel for the E's and the A pixels. And now once I do that, then I have all my pixels, because this is an A pixel, by the way, this one here. This one here is an E pixel. Questions? Okay, question. When you say a training window, yes, absolutely. You have this training window size is your design parameter, and as you are moving around the image, every time you move around, you would use a different set of alphas because the relationship between the pixels in different regions in the image will be different. So now you can imagine if you have very, very large training window, then you are really inserting some kind of estimation errors. If you have very, very small one, they are paying too much for processing. So there is a balance in between the two extremes in this case. But the answer question is yes. So now all of these basically kind of slides that I have kind of explain what I just talked about in more detail. And now once you have you just plug into the least square solution that we found, and then you find the values for these alpha. So now some remarks about, just make sure I have, okay, I have 1 minute. Yes, I have 1 minute. Oh, okay. Yeah, I can finish the examples in 1 minute. So it is computationally expensive. So you can imagine for high definition images, you will have a large training windows. So it becomes really an expensive algorithm in this case. Also, the NIDI that in the original paper from almost 19 years ago, there is no constraint in the coefficient. However, there are rare follow-up algorithms on NIDI where if you have a constraints on these alphas to be the sum to be equal to a 1, it performs actually better for natural images. But that's just comments. So these are examples from the original paper. A is the original airplane image, and then B is reconstructed using bilinear interpolation, C by bicubic interpolation, and then D is by the NIDI algorithm. So you can see around the wing edges in here, around here, there is a better performance in the NIDI compared to the bilinear and bicubic one. You go to the curve domain, and in this case, for example, you do the processing in the Carl difference space. You remember the Carl difference when we have these ellipses in the Carl space where the Carl is not the just noticeable difference between the Carl is 0 in the ellipses. So this is the Carl difference space in here. And these ones are using the NEDI algorithm. So you can see there is really a very nice trade-off between blurriness, as we have in here, and between basically overdoing it in the bicubic relationship in here. So you are maintaining a very nice texture. It's very difficult to differentiate between these two images perceptually, but you can see there's some sharpness around here to the NEDI algorithm compared to the one on the left-hand side. And if you look at this example in here, these are the samples after we sampled 56 by 56 images using NEDI, using the bilinear, bicubic, and the pixel replication. And you can see basically, all of them perceptually at least, the NEDI is really the best performance. And this is just a teaser for next lecture. The PSNR is the lowest, 18 dB. By the other ones, 21, 21, 20 dB. Don't let that trick you. So we'll study next time why do we rely on something like structural similarity to better reflect the quality than PSNR. But that's just a teaser for next lecture. Here are some examples. This original image for tiger. What you need to look at is the sharpness around here, and around the whiskers in here. So the left is the pixel replication, and then you can expect there's quite a bit of discontinuity. You can see there's just like floating kind of pixels. It's very, very rough here. And on the right-hand side is blurry. Again, the PSNR will look at those on Thursday. And here is the NEDI, the NEDI compared to the bicubic. You can see from where I'm looking at, definitely the one on the right-hand side is better quality than the one on the left-hand side in this case. And finally, what I want to mention is I put one of the papers in the project is about super resolution and interpolation. I put the PDF also on the next to the lecture resources for today's lecture. And the main message is there in that paper. They have, of course, a convolution neural network. However, the main idea is that they are doing interpolation at many different scales. So imagine that you are having all these images in here, and they're doing interpolation from each one of them, right? And then you are combining them all together at once. And this multi-scale processing is extremely useful in processing. And that should be really kind of a hint in your project. You want to think about there are certain features in the image that are represented very well at a certain scale, but not at the other scales. So if you don't really do it at the right scale, you miss out on these features or content. So if you have a smart combination of all these features at different scales, then you will have a much better algorithm in this case. Okay, there is a question here. Let me go back to the any-die method. Question is about, I didn't understand what was the difference between pixels inside training window and outside. So the training window, this is the green one. This is the one you use to find the values for your estimator, which is alpha 1, alpha 2, alpha 3, and alpha 4, right? So now, any of these new pixels, either they are A pixel or B pixel or E pixel, any of these new pixels, you use the same alpha 1, alpha 2, alpha 3, alpha 4, as far as you are within this window. As you move the window to a certain other part in the image, then you have a new training window. You have to run the training again, find the new values for alphas, and then you use those to find the new intensity values for the high resolution pixels in that window. I hope this helps. And so this will conclude the lecture, and I will have office hours tomorrow if you have more questions. And the way you decide on the size is really a design parameter. So it depends on the statistics of the image. Is it smooth image? Is it too much detail in the image? Is a design parameter, the window size. All right, thank you. And we'll see you Thursday, if not tomorrow. Thanks, bye.